Okay, we're going to be continuing to look at exponential equations. We're going to be looking at both exponential equations and exponential inequalities today, talking about how to solve equations when you have a variable in the exponent. Okay, so we're going to start with something pretty simple here. For example, if you have the equation 3 to the x, and that equals 3 to the fifth, as long as your base numbers, we called those the multipliers in the previous section, as long as those are the exact same number, then it would stand to reason that your exponent that you have on the left would have to be equal to the exponent on the right. Okay, so if we're saying 3 to some power equals 3 to the fifth power, then I should be able to set these two exponents equal to each other, as long as their bases are the same, and then I've solved the equation for x. This missing exponent over here would have to be a 5. Okay, so I think the goal here with these problems is to try to see if you can make both of the base numbers the exact same number. Now, if they're different, we cannot set the exponents equal to each other. But if we can manipulate one or both sides so that they have the same base number, we can then set their exponents equal to each other. And that's what this is saying. If the two bases are equal, then their exponents must be equal to each other. And so that's what we're going to try to do. And here's the tip that I would give you is typically you are going to manipulate the larger base number, okay? Not always, but usually the larger base number, you can manipulate that to make it look like the smaller base number. So I'm going to leave the left side, since that has a smaller base, as 2 to the x, and I'm going to see if I can get creative and come up with a different way of writing 8. And for the moment, just ignore the fact that the exponent is a 3 on that 8. You want to ask yourself, is there any way that you can rewrite the number 8 so that it could be written as 2 raised to a power? Okay, 2 2's makes a 4, but if I do 3 2's multiplied in a row, that's when I actually get an 8. Okay, so all I'm really doing here right now is I'm just taking the 8 out, but I'm really keeping an 8 in my problem. I'm just writing it a different way. I'm writing that 8 as a 2 cubed. Now, I haven't addressed the fact that that 8 is also cubed, so I need to keep that 3 out here on the parentheses. So if you look at what we have here, I'm still really saying that I have an 8 that I'm cubing. Okay, now when I have it written like this, I want to go ahead and try to simplify this right side. So I'm going to take the 3 that's on the outside of the parentheses. I'm going to go ahead and distribute that to the 3 on the inside, and that's going to make the new exponent on the 2 a 9. Okay, now I have this situation. My two bases are now equal. I have a 2 and a 2. So that means I can now take their exponents, and they must be equal to each other. So I can take the x on the left, set it equal to the 9 on the right, and there I have solved the equation. Okay, if you ever wanted to check your answer, you could go back up to the original problem and try it. Type in 2 to the 9th. Compare that number to what you get when you type in 8 to the 3rd. It should be the exact same number. Okay, so let's try it again here. Keep in mind our little tip here. Our tip says you typically want to manipulate the larger base number. So on this example, the larger base of these two bases would be the 9. So I'm going to change a 9, and I want to try to change it so that it matches the same base number that I have over here on this side, which is a 3. So I want to see, can I write the number 9 as 3 to a power? And absolutely we can. We can write the number 9 as a 3 squared. So this is still representing a 9. But the original exponent that was in the problem, the 2x minus 1, I want to keep that there in the problem on the outside of the parentheses. Okay, just like we did over here then, we distributed and we multiplied the two exponents together. Here, we're going to distribute the 2 to both of these terms right here, and that's going to make this 3 to the 4x minus 2. Okay, now I have the situation where the two bases are equal, So that means the exponents must be equal to each other. So I'm going to set the exponent on the left equal to the exponent on the right, and I'm going to go ahead and just finish solving this equation for x, and I end up getting that x would have to equal the number -1. Okay. Again, pretty easy to check. You could just substitute -1 back in, type that in the calculator, substitute -1 in for the x here, type that in. Should get the exact same number on both sides. Okay, now this next one's a little bit more challenging. We said here that typically you manipulate the larger base, but I don't think that we can express the number 8 as 4 raised to a power. Like here we could turn the 8 into a 2 cubed, but I don't think we can write 8 as 4 to a power. 4 to the first is 4. If I go 4 squared, I've already passed 8 up. That would be 16. And so in this scenario, we're actually going to have to change both of the bases. We need to bring both of the bases down to a smaller base number that would be the same. So we could write 4 as a 2 squared, and then I want to keep the original exponent on the 4 outside the parentheses. And then I could write the number 8 as a 2 cubed, just like we did over here. Okay, so essentially I changed that 4 into same thing, 2 squared, and I'm changing that 8 into 2 cubed. Okay, so now I'm going to distribute this 2. That's going to make this 2 to the -4 minus 2. And over here I really don't need those parentheses there. That's just 2 cubed. Okay, now I'm going to take the two exponents, now that the bases are equal, and I'm going to go ahead and set the two exponents equal to each other, and then I'm going to solve the equation for n, and I end up getting that n is equal to -5/4. Okay, so these problems are going to be given to you in such a way that you should always be able to manipulate either one or both bases to get them both to be exactly the same. Okay. When we run into problems where we can't do that, that's when we are introduced to logarithms, and logarithms will help us. But in this section, we should be able to do that just fine. Okay, so let's take a look at very similar problems, only with inequalities. And I think you'll notice one little difference about these problems is some of these have fractions in them. So what you're going to want to do first, if there's fractions, you're going to want to take what is in the denominator and you're going to want to pull that up to the numerator. Now remember our rules for exponents here. The exponent on this 3 as well as that 8 is to the first power. Okay, we want to pull it up to the numerator. When you move things from a numerator to denominator or vice versa, what it does is it changes the exponent so that it's the opposite sign. So instead of being 3 to the first, when we pull it up, it's going to be 3 to the -1st. Same thing over here. If I pull that 8 up, it's going to be 8 to the -1st. Okay, well, just the act of me pulling this 3 up, now I can see, okay, these two bases are exactly the same. So that means instead of setting the exponents equal to each other, I want to use the inequality symbol that's in my problem. I'm going to put a less than symbol in between. But I'm just going to keep solving this the same way that we would solve as if it were an equation. The only subtle difference that you want to be watching for with inequalities is if you ever divide both sides of an inequality by a number that is negative, it does cause the symbol to flip the opposite direction. Okay, so here we are again with this one. We're needing to change the bigger number, the 8, down into something that would match the smaller number. We had the same scenario right up here where we had to switch the 8 into a 2 cubed. Okay, so we're going to write this as 2 cubed, and then we're going to keep that exponent of a -1 there. I'm going to multiply these together. This will be 2 to the x plus 2 is less than 2 to the -3rd. Okay, now the two bases are the same, so I'm going to take the exponent on the left and set it less than the exponent on the right. Just solve for x, and I get x is less than -5. Okay. All right, let's go ahead. We're going to flip over here. Now, your assignment that goes along with this is actually just the assignment that was listed at the top here. It's going to be worksheet 7.2a, but we're going to be doing both sides here to this notes page. Okay, what we're going to be looking at here on this side is we're going to be looking at what's called a compound interest formula. Okay, the compound interest formula is used a lot in banking, and it's really important in this formula that you understand what all of these variables are representing. So I'm going to have you label some of these here first. The A represents the final amount. So if you guys have ever deposited any money into a bank account, and then, hopefully it collects a little bit of interest. This A represents kind of what your account balance is. The P stands for principal. And if you remember in the previous section, when we had the equation y equals AB to the x, we said that A represented like the initial population. Principal is a banking term that just means the initial amount, like how much you would have deposited at the very beginning. Okay, the R is the interest rate. You may want to make a note to yourself, though, that when you make a substitution in for the interest rate, it's often given as a percentage in the problem. You will need to always convert that into a decimal, though, when you put it into the formula. Okay, there are two places where there are n's. You'll plug the same number into both places, but the end represents the number of times that the interest the number of times that the interest is compounded per year. Okay. So you're going to hear words like it's compounded quarterly. Okay. That means n would be 4. If it says daily, that means n would be 365. Okay. You have to figure out how many is that referencing in one entire. Annually means just once in a year, okay? It is typically to your advantage as an investor to have the interest be compounded most frequently. So quarterly is better than annually, daily is better than quarterly. It's when they give you your interest into your account, which obviously would make your account grow, and then from there, that extra added growth, now they're compiling the interest onto that. And so the more frequently they give you the interest, the faster that your account balance would grow. Okay, and the last variable is this T, which represents the element of time. Typically, that's years with the problem. Okay, so let's go ahead and see if we can work through just a couple of these problems here. It says an investment account pays 4.2% annual interest compounded monthly. Okay, so we want to take note here that it's compounded monthly. Okay, that's going to be 12 times a year. It says if $2,500 is invested in this account, what will be the balance after 15 years? So I've kind of highlighted some of the key components here. We want to make sure that we're getting these plugged in the right spot here. The question is ultimately asking for the final amount. They're asking for A. So we're not going to be plugging a number in for the A, but the principal amount, the initial amount, is that $2,500. So we're going to plug that there. Oops. All right, then we have 1 plus the interest rate. Now be careful, this is given to you as a percent. You're going to need to swing that decimal point 2 places to the left so that we're really inserting 0.042 in for the R. Okay, there are 2 places for the N. Remember, N stands for the number of times the interest is compounded in 1 year. Well, if it's compounded monthly, they would be giving you the interest 12 times a year. And then the T, which is also in the exponent, is the number of years that you're going to let the money sit in the account and grow, and that is 15. Okay, so what we would do next, and you're going to want to make sure that you practice typing this in, because honestly, where most people make their mistake is how they're typing it into the calculator. Okay, I typically recommend typing it into smaller pieces rather than trying to type it in all at once. I like to type in everything in the parentheses and hit enter. And then I raise that to the, and you might, if you have an older calculator, you might have to put this in parentheses here, raise it to the 12 times 15 power, hit enter, and then at the end, multiply that answer by 2,500. Okay, should be getting this answer 4,688. Okay, you can see the next example I went ahead and did for you just so you have another one to look at there in the notes. Let's go ahead and look at example 3 here. This is talking about Kristen. Now this doesn't feel like this is a banking problem necessarily, but in this problem it says that she starts an experiment with 7,500 bacteria. After 4 hours, there's 23,000 cells. We're asked to write an exponential function that could be used to model the number of bacteria after X hours if the number of bacteria changes at the same rate. Okay, so let's see what we have here. We know that she's starting out with 7,500. Okay, that's kind of like the principal amount, or that would be the initial amount. And if it's not really a banking problem, you can go back and kind of, think about that. Really, this is what our formula is here. Okay, now remember, A is the initial amount, Y is the final amount. So it says after 4 hours, then the final amount was the 23,000. So I'm going to plug that on the left. Okay, it feels like the piece of information they're really not telling us is they're not telling us what the growth rate is. Okay, we don't know that. So I'm going to leave that as a B. That's my multiplier, 1 plus my growth rate. But we do know that it took 4 hours to grow from 7,500 to 23,000. So I'm going to plug the 4 in there. Now what we're going to have to do is we're going to have to use algebra, and we're going to work backwards to get what the multiplier is. Our goal is to solve this for that B. Okay, so the first thing we need to do is divide both sides by 7,500. Okay, so we want to divide 23,000 by 7,500. That's going to give us, I'm going to switch that back into a fraction because I really don't want to do any rounding until I get to the end. Okay, so if I type this into the calculator, switch it back into a fraction, here's the fraction I get. Now I want to solve this for B, but this is B to the 4th. So what I'm going to need to do is I'm going to need to take the 4th root of both sides here. So on the calculator, you're going to press the number 4, then you're going to hit the math button, and you're going to pick the option that has like the little X right there. Okay, and it should automatically put a 4 in then where that X was. And then you would type in, taking the 4th root of the fraction, 46 divided by 15. At this point, it's okay to round. We're going to say that's 1.32. Okay, so now I know the B. So I'm going to go ahead and write my equation. Y equals, I'm going to put the initial amount of bacteria, 7,500. I'm going to put the B value in, 1.32. And then I'm going to leave my X, my time right there. This is my working equation that I'm going to use to answer part B. It wants to know how many bacteria cells could be expected in the sample after 12 hours. Well, my exponent of my X is representing hours, and my Y is representing the final amount. So I want to know what's the final amount after 12 hours. I'm simply going to substitute a 12 into my equation. And I'm going to get roughly 209,869.07 bacteria cells. Okay. So that one was a little bit different because they gave you an initial, they gave you a final, they gave you a time. We had to work backwards to get the multiplier in order to build the equation to answer the second part here. Okay, almost done here. Let's look at example 4. It says a manufacturer distributed 3.2 million recycled aluminum cans in the year 2005. Now it's the year 2010, and look, he hasn't recycled very much at all. It feels like his business might be dying here. He's only recycled 420,000 cans. Assuming that the recycling rate continues, write an equation to model the distribution each year of cans that are made from recycled aluminum. Okay, so again, this is going to be very similar to the previous problem. We want to take what was the amount of recycled cans here that he did initially. Okay, well that was the 3.2 million. Okay, I'm going to go ahead and fill it. 3.2 million would look like that if we wrote it out. Okay, all right, I don't know what the, oh, I got this backwards, I'm sorry. Okay, initially, the 3.2 million should go over here. The final amount, this is in the year 2010, and it shrunk all the way down to only recycling 420,000 cans. I don't know the multiplier, but I know that from 2005 to 2010, the time, and that's what my exponent is, was 5 years. Okay, so I'm going to go ahead and solve this for B. So I'm going to divide both sides by 3.2 million. Okay, so we'll type that in. I'm going to switch that back into a fraction. That's 21 over 160. That's going to equal B to the 5th. And then I'm going to need to do the 5th root of both sides. Okay, again, you're going to press 5, the math button, option 5, and then you will type in 21 divided by 160. The B is going to come out to 0.67. So now I'm going to write my equation. Y equals initial amount, that's how many he recycled back in 2005, my multiplier, 0.67, and I'm using x as the time. Now, to answer part B, how many cans from recycled aluminum could be expected in the year 2030? Remember, our original year was 2005, so to go from 2005 to 2030, that would be 25 years later. So I'm going to want to substitute a 25 in for my time, and it seems like his business was really declining quite a bit here. So if we plug in 25 for the exponent, oh, he's almost out of business. For the whole entire year, he only recycled 143.56 cans. Okay. All right, the last part to this, and I have a probably 2.5-minute video that's on my webpage on the tab titled TI-84 calculator videos to show you how to run an exponential regression. All you're essentially going to do for an exponential regression is you're going to put the x coordinates into L1, the y coordinates into L2. You're then going to press the stat button, followed by the calculate menu. You're going to go all the way down until you see, for me it was option 0, but till you see the option exponential regression. Okay, you're going to pick that and you're going to follow through everything else exactly the same. Okay, it will spit out then an A and a B value for you to substitute in there to build your equation. Okay, if you're unclear on that, I have screen captured a calculator screen and talked through a 2.5-minute video. If you go to that tab on my webpage, it'll walk you through how to do this problem. All right, I believe that your assignment that goes along with this video is on my webpage. If you don't have a hard copy, it's worksheet 7.2a.